All right, so here are some definitions that are going to be important for us leading into calculus and how the idea of a limit is related to the idea of a derivative and the main idea that we're doing in our first unit of calculus. So a secant line is a line that cuts through a curve. So if we had a parabola, any line that cuts through that curve would be a secant line. So here's an example of a secant line. Usually at 2 points, but depending on what function it might cut through at 3 points. You could have one that cuts through that doesn't go through another point, but this is the basic idea of a secant line. The reason that's important is because a tangent line is a line that touches a curve usually at only 1 point and usually doesn't cut through that point. There are some exceptions to this, but for our main idea, here's our same parabola that we had before. And you did back in grade 9 tangents to a circle, and that's when a tangent touches a circle at only 1 point. Same thing here. You have a tangent touching a parabola only at 1 point. Just so you can see an example of, here is an x cubed graph right at 0, 0. The tangent at 0, 0 actually cuts through it. So it's kind of an interesting situation there. So tangent lines tell us something about a graph. A tangent line tells us the slope of the graph at that instantaneous point, and it gives us a rate of change, because that's what slope is, at that point. That's what we're going to be leading towards as we get into calculus, because the first bit of calculus that we do, derivatives, is all about rates of change. So when you're looking at an average rate of change, that's the idea of figuring out the slope of a secant. So for example, if I was driving from here to Portage, I might have this time speed. My car starts off not going very fast, but then I pick up speed, stay a certain speed, and then slow back down when I get there. Maybe I'll do distance. Maybe I'll do distance instead here. Let's go. Displacement distance. We'll assume we don't come back home in between, but we'll do distance. So here we are. We're traveling. How far is it? How far is it to get there? Maybe 50 kilometers away. And we don't go very fast in the first little bit. Then we go really fast. Have to stop. No, that's speed again. Have to stop because we get a speeding ticket. Don't go, and then we get there. Okay? So let's say in the end, I travel 50 kilometers, and it only takes me 30 minutes. My average speed would be figuring out what that slope is. And if I wanted to figure out what the slope of that line is, slope is just rise over run. And my rise is 50 kilometers. My run is 0.5 of an hour. And I could convert this to saying, well, that's the same as 100 over 1. So my average speed was 100 kilometers per hour. That's probably why I got that ticket to begin with, because if I'm averaging 100 kilometers an hour, that also counts the beginning when I wasn't going very fast or I was driving through the city for a little bit. So once I got on that highway, I must have been going faster to get that. And especially because how long would it take me to get a ticket? That's probably 15 minutes of time just to get the ticket. So I must have been going really fast. Did I time travel this little bit here? The straight line is because I wasn't, that's when I got caught by the cop. Because I'm not actually traveling any distance during that time. I'm sitting in my car going, oh no, right? So we've got that idea happening right there. Now, if you wanted to find the instantaneous rate of change, that would be finding out how fast I was actually traveling at a specific point. So now we're going to go back to our graph here. Yeah, this graph is really bad. But anyways, if I pick a point right here, and I would draw the tangent of that, okay? And I would figure out the slope of the tangent at that point. Looks like I've got a run of about 1 minute. And if this was 50, let's say this is 40 kilometers. So I have 40 kilometers over 1 minute. If we change that to kilometers per hour, I'd have to have 60 minutes there. I'm surprised the cop caught me. Here we go. That would be that's my superjet vehicle. I was going 2,400 kilometers an hour at that specific point. So if we can find our tangent and then we find our slope of our tangent, that's what the speedometer on my car was saying at that point. A very special car to be able to show that. So my graph probably isn't that realistic, but I think it gives a good example of the difference between an average rate of change, where you're taking the slope of your secant line, and your instantaneous rate of change, where you can draw your tangent at a specific point, calculate the slope of that tangent at that specific point, and then you'll be able to say, I know at about 15 minutes that your speedometer was saying 2,400 kilometers per hour. I don't know what equation they use to calculate tickets, but I'm sure that would be a very, very bad one. So that's the difference between an average rate of change and an instantaneous rate of change. And so we talk about rate of change as a slope. And here are some different words for slope and some different symbols for slope. You might remember the slope formula from grade 10. There it is again. It's rise, right? This was your rise over your run, your difference in your y values and your difference in your x values. Your gradient is just another word for slope. You might hear that a little bit more on roads. They talk about a gradient of a road, how much it's rising over a certain amount of time. And if the gradient is too much, sometimes they give warnings. If you've driven through the mountains, sometimes they have a little percentage sign saying up ahead the road is going to be really steep, so just be careful. Have you seen this delta symbol before? It just means change in y over change in x. And when we do derivatives, we'll find out that all of these ideas of slope is actually our first derivative, dy over dx. So we kind of did this already, but we can make up another example here. We can do distance here and time here. This time we'll just take a bus driver. Bus driver is driving to school, starts off on his day, after a certain amount of time picks up a kid, so he's not going anywhere, then drives a little bit further, picks up another kid, drives a little bit further, and stops at the school. So let's say the time here is in minutes, and we'll go 10, 20, 30, 40, 50. nicely drawn scale. Everything is perfectly equally spaced. Nice. Oh, I guess maybe we'll do time in, since my value's here. I'll just do 1, 2, 3. Can pick up kids really quick. It's only, could be hours, but I'd hate to pick up a kid and wait a whole hour till they get on the bus. So let's put this time in minutes. So we can calculate the average rate of change for the first one here if we went from 1, which is right there, to 3, which is right there, and we draw our secant line between those 2 points. Wow. We know that our run would be 2, and if we would estimate our rise, does it look like about 0.5 there? So if we figure out the average rate of change, for this first one, it's going to equal 0.5 over 2, which is equal to 1/4. What should our distance unit be? Meters? Kilometers? So this bus is going to drive 1 kilometer in a minute? Is that reasonable? 1 kilometer, 1 meter in a minute? I like meters. It's a really slow bus. All right. So these kids are waiting to get on the bus. One's here, one's here, and one's here, right? And the bus is like, boom, and it takes 1 minute for that. You're just like, come on. And you're waiting. Excellent. I like this. Yeah, the kid can't walk to get on the bus. No, they wait. And then the bus inches forward again. Nice. So from the time it picks up the first kid to the time it gets the second kid and actually starts going again, and it looks like we're only picking up 2 kids on this bus ride for the entire time, the average rate of change is 1/4, and that is meters per minute. So every minute it's on average going about this far. Nice. Now, if we wanted to find the average rate of change from 1 to 4, well, then we would go 1, and we would do 4, and here our run is 3 now, and it looks like we're going up 1. So that would be the average rate. It's a little bit faster at this point. The bus is really moving. 1/3 of a meter per minute. But if we would look at from 4 to 5, wow, 1/1 meters per minute. Really, really moving along. And you could figure out what the speedometer actually changes if you wanted to change that to kilometers per hour. See, is that really fast or is that still quite slow? So all we're doing is that average rate of change is just looking at the slope or the gradient between 2 points. If we want to find an instantaneous one, we have to come up with some way of figuring out the slope of the tangent at a specific point.